Alright, so Boyle's law gives us the relationship between pressure and volume of a gas if temperature and amount are held constant. Here, I have written the mathematical form of his law, but first let's talk about how Boyle got there. So, suppose the volume of a container is increased. This means gas molecules have farther to go and they will impact the container walls less often per unit time. So, the gas pressure will be less because there are less molecule impacts per unit time. So, if volume is increased, then pressure decreases. Now suppose we decrease the volume of the container. In this case, the gas molecules will have a shorter distance to go and thus will strike the walls more often per unit time. This results in pressure being increased because there are more molecule impacts per unit time. So if volume is decreased, then pressure increases. What I have talked about can also be illustrated by this equation. Boyle discovered that the pressure-volume product will always be the same value if the temperature and amount of gas do not change. K is just a constant, but you will never be asked to find the value of K. It just shows that this is an inverse mathematical relationship. As one quantity goes up, the other one goes down. So many times you will be asked to find either the final pressure or volume in a system where the initial pressure or volume is changed. To solve these types of problems, you can use Boyle's law. If the initial pressure-volume product is K, then the final pressure-volume product must be equal to K. Since K is just a constant, you can write it as initial pressure times initial volume equals final pressure times final volume. In most textbooks, you will see this equation written as P1V1 equals P2V2. It's the same thing. Just remember that this is only true in conditions where temperature and amount of gas do not change. So let's try a problem. 5 liters of a gas is at 1.28 atmospheres. What pressure is obtained when the volume is 10 liters? Okay, so we can solve this by inserting values into our version of Boyle's law. P1 V1 equals P2 V2. We are given the initial pressure and volume, so 1.28 atmospheres times 5.00 liters equals, we are not given P2, but we're trying to find the final pressure, so we can keep that as P2. And we know the final volume, which is 10.0 liters. Since we have one unknown, we can solve this equation using algebra. We get P2 equals 1.28 atmospheres times 5.00 liters, all divided by 10.0 liters. And the liters cancel out, and if you plug this into your calculator, you should get 0.64. Since the problem gives us 3 sig figs in its values, we must make this 0.640, and the unit on that would be atmospheres, ATM. So there's our final answer. You have to remember that you can only solve problems this way if temperature and amount of gas do not change. Okay, here's another problem. 2.5 liters of a gas was at an unknown pressure. However, at 1.02 atmospheres, its volume was measured to be 7.25 liters. What was the unknown pressure? So I encourage you to try this problem on your own before I do it out. Alright, so I'm assuming you have done it. You probably realize that this problem was similar to the last one. This time, however, we're being asked to find the initial pressure. Since we are given the initial volume and final pressure and volume, we can find this using Boyle's law. Remember, I'm assuming that temperature and amount are held constant. So I'll use a green pen this time. P1V1 equals P2V2. We want to find P1, so I'll leave that as it is. V1 is 2.50 liters. P2 is 1.02 atmospheres. And V2 is 7.25 liters. We want to find P1, and so that would be equal to 1.02 atmospheres times 7.25 liters, all divided by 2.50 liters. And once again, liters cancel, and P1, plugging that into my calculator, equals 2.958 ATM. But once again, we are given 3 sig figs, so that should be rounded to 2.96 ATM. Hopefully you got that. Thanks for watching.